Okay, I'm Zheng Kai. Yeah. Mm. I'm
Yes,
a
Professor.
Hi, thanks. I'm an associate professor at the Department of Astronomy at Tsinghua University. Today, I would like to introduce you to give you a guide tour of our the probing of our universe, and introducing some method of probing the first stellar light in the early universe. So why it is related to your study here? I think right. It is it's a long time ago, like thousands of years ago. People always long for probing the universe to understand more and more about the universe. I think that's also global stuff, and also probing through the probing of the universe, different countries can also cooperate and collaborate. So I also was trained in the US. I was obtained my PhD from the University of Arizona, and also spent 4 years as a postdoc scholar at the University of Santa Cruz, California, Santa Cruz, as a NASA Hubble Fellow. And then I back to Tsinghua as a faculty. So a lot of my research is also learned from US, and I also have a lot of international collaborators. Okay, so I hope you can enjoy the talk. So what is the universe? So if assuming if I introduce a kid to everybody, if I introduce a student to everybody, I think people will care about what's your name, what's student's name, how old are you, how tall you are, what's your weight, and how many family members do you have, and what are you coming from, and what is your hobby, stuff like that. So let's also ask the universe the same questions. So what is the meaning of the universe? I think about more than 2,000 years ago, and Chinese philosophy gave the definition of the universe. They claim that up, down, north, south, east, west, past, and present, it is the universe. Basically, they suggest that the space and time are the universe. The universe in Chinese means 宇, this character means space, and 宙 means time. I think that's a pretty, although the definition is pretty old, but it's a pretty advanced understanding, because the general relativity, Einstein view of the universe is trying to make sure they understand correctly about the space and time. So how old is the universe? I think right now our current study indicate that the universe has already 13.7 billion years old, but still very young, because we cannot see because the universe still accelerating, expanding. So we didn't see any sign of that the universe like decelerating or not expanding. So the universe is still accelerating, expanding, so that I think the universe has still a long future ahead of us. So how tall the universe is, if you use in a unit of a meter, then the universe will have yeah, this number I showed here. I don't know how to read the number out, but there are 26 zeros. So the size of the universe currently, the observable universe is 13.7 billion light years, because the age of the universe is only 13.7 billion years, and the speed of light is finite, so we can only see possibly the 13.7 billion light year, the size of the universe, but the actual universe has already expanded far beyond the scope that we can possibly see. And only in these, and also in these 13.7 billion light years, we can only see a tiny fraction of the universe, because people may know that dark matter, dark energy, stuff like that, and the normal matter in the observed universe, so only like 4%. Okay. So what's the weight of the universe? So we normally don't say weight. We sometimes say the density. So the density of the universe is very, very thin. Seems like I also don't know how to read out the number, but there are 30 zero if you use the unit of a gram per cube centimeter. So remember that our like air. So you think that the air has a really lightweight, but the air is far more weighted than the density, has a much higher density. The air has a density of 0.004 gram per cube centimeter. So it's like 10 to 27 times the density of the universe. So the universe is just a perfect vacuum. A perfect vacuum. It's so perfect that in that kind of vacuum on large scale, you already like, it's not the gravity on large scale not dominating, because the density is so low. And there is a term called dark energy. Dark energy basically like function in the all opposite direction compared to gravity, like dominant the universe. So the density, the matter density of the universe is so low. So how many family members do the universe has? So if we say, like, in the universe, if we see a star, is a family member. If we say inside the universe, the unit of family is star. So how many your family members? So currently we have detected at least 100 billion galaxies. We have already observed. So there may be far more than that. And every galaxy, roughly speaking, has 100 billion stars. So for example, our Milky Way is more than 200 billion stars, suns out there. So I think the universe at least contain 10 to 22 stars. How to fill 10 to 22? If you fill the Earth with all this sand, then the number of the grain, sand grain, is about 10 to 22. So the stars is more than the number of the sand grain on Earth, basically. Yeah, so many. So where is the universe coming from? So we know that from the observations I gonna talk about, the universe come from a Big Bang. So it is more or less consensus right now. The universe should many parallel observations have proven that the universe is expanding, and the universe should come from a big bang. The universe has a starting point. So does the universe has any hobby? So I think if we say the universe, if the universe has some hobby, I think the movement, like the kinematics, is the basically doing exercise, is the hobby of the universe. There are a lot of the universe is very energetic, like to do a lot of exercise. Like although we sit here to listening the lecture, we actually move very fast. So one day we can move for 40,000 kilometers because of the rotating of the Earth. So also the Earth is also rotating around the sun. The velocity is 10,000 kilometers per hour, much faster than any plane. And also our solar system is also orbiting around the center of the Milky Way. And 1 hour we can travel almost 1 million kilometers. So 1 second is about more than 200 kilometers. So move very fast. So the universe is very energetic. Like so the energy is really vast. So, and also our Milky Way is contained in this so-called local group, right? And this local group is also orbiting around a supercluster called Laniakea supercluster. So the scale is about 100 million light year. And if we move farther away, if we move like if we see the whole universe from the top, like if this page has a scale of 3 billion light years, about 3 billion light year, we will observe this like filamentary structure filling out of the space. So these filaments are dark matter filaments, and inside the dark matter filaments there are also the baryonic matter, so like gas and stars, and the galaxy live in the intersection of the filaments. So just like our when we look down upon a city, so that if we sit on a airplane, and if we see like the city, the big city of Beijing, Beijing is just a reside in the intersection of a major traffic road, right? So the universe also has a geometry like this. So, right, there's a lot of similarities between the large-scale structure of the universe and yeah, many other things, which is quite interesting to explore more. So let's take a look at the scale again. So here I have a video show. Here is one light day. You already travel at the boundary of the solar system. And if you go 1 light year, you have already come into the scale of the nearby stars. And if you travel further, tens of thousand light year, you will sit in the spiral arm and see the whole Milky Way. And if the million tens of million light years, you will see many galaxies, same as the Milky Way. If you see the billion light year scales and the cosmic city like galaxy reside in the intersection of these filaments. So that's about the space. How about the time? The time I already told you at the beginning of the talk. The universe has an age of 13.7 billion years. So how to feel that? Like if I set the beginning of the universe as a January 1st, I think, and then in February 7th is the formation, the starting formation of the Milky Way, and the Earth forms on September 3rd, and the earliest life in the Earth happens on September 22nd. And the Cambrian explosion, because the animals start to have eyes. So if they have eyes, they can search for food. And then there is the Cambrian explosion. So that the eye is very much important. And the telescope is the big eye of our human being. And I believe they can bring us to further the development. So the Cambrian explosion happens on December 17th, and the rise of the dinosaur is on December 26th, and then the dinosaur extincted on December 30th, basically. And then basically our human being evolved at 9 o'clock p.m. on December 31st. And 25 seconds ago is the rise of agriculture, and 11 seconds ago is the pyramid built. So all these Kepler principle, Galileo discovery of the telescope, and all this like the Earth is not the center of the universe. The modern, basically the industry, all these 400 years development is only 1 second in the watch of the entire universe. So the universe has a vast. So that's just to tell you how can we feel the 13.7 billion years. So the 400 years as the development of the human being is just a 1 second. So so the human history is just a moment, a short moment. So and then we can come that's about the background. And today our main task is to introduce everybody a survey to search for the highest redshift galaxies in the early universe. So we need to understand what is a redshift, because we already know that the universe is expanding and the universe seems to be stationary, but it's not. It's expanding. So 100 years ago, there is a great debate. The great debate what? It's a great debate the nature of the spiral nebulae. So people has 100 years ago through the telescope, people has already discovered there are many stars in the Milky Way, and there's also some spiral nebulae, the diffuse source also themes in our Milky Way. And the Shapley is the director of Harvard astronomy department. And he basically claims that the Milky Way is the universe, and the diffuse nebulae are the star clusters inside the Milky Way. And the Curtis is the director of University of California. So at that time, he thinks that the nebulae is just like Milky Way. They just looks small because the distance is very large. So they are debating about the two solutions of the spiral. It's about the nature of the spiral nebulae they have observed. And Edwin Hubble has successfully solved the puzzle, and he basically confirmed that the spiral nebulae is just like our Milky Way. They looks very small, just like star cluster, because it is so far away. So, and also he established this Hubble law. So in the sense that the farther the galaxy away from us, the higher the galaxy, the higher the velocity of the galaxy receding from us, basically running away from us. The farther the galaxy is, the higher velocity that the galaxy running away from us. Basically, this is so-called the Hubble law. So Hubble law, as long as you know the Hubble constant, and then you can measure the velocity of the galaxy running away from us and translate it to the distance of the galaxy. So how to measure the velocity? The Hubble basically use the spectroscopy, because if you spread the light across the wavelengths, you can feel a lot of the emission and absorption line. Through this emission and absorption line, you can get the velocity, just like the Doppler effect, the Doppler effect. So the changing of the wavelengths can tell you the velocity. So and then you can feel that the higher velocity it is, the higher basically the absorption and the emission move towards the red, basically toward longer wavelengths, so toward the red. So Hubble named these phenomena as the redshift. So the higher the redshift is, means the higher velocity the galaxy running away from us. That means the farther distance the galaxy is. So then the Hubble successfully translate the problem of measure the distance into a problem for measuring the redshift. So then right, right, basically in the year of 1999, in the year of 2000, the three independent group redoing the exercise of what Hubble has done, but they use much more powerful telescope, and they measure up to the redshift of 0.5, and it is a half of the size of the observable universe. So and they find that the distance and the velocity or the redshift is not proportional. It's not proportional. It's proportional when the distance or the redshift is small. But if the distance or redshift is large, then the universe is actually accelerating, expanding. So they basically discover the so-called dark energy that drives the universe accelerating expansion. So they win the Nobel Prize in 2011. So then we know after their observations, we know the universe has 4%, only 4% of normal matter, and 20% of the dark matter, and 70% of dark energy, something like that. So then we have the overview of the expansion of the universe. As I already explained, that the higher the redshift is, right, the wavelengths will move more and more toward the red. That means the velocity of the galaxy is higher. That means the distance between the galaxy and us is large. Basically, so the higher, because the speed of light is finite, so the higher the redshift is, that means the galaxy is farther away from us. That means the universe we observed is younger. It's younger. So that's a overview of the expansion, the cosmic expansion. So we try to observe two astrophysical objects. One is the galaxy, one is a quasar. Maybe, is there anybody know what quasar is? Have anybody heard about the word quasi-stellar object? Is there anybody who has heard any people talking about the quasi-stellar object. Right, okay, it's fine. So,
Well,
oh, yes, yes. Is there anybody speaking?
I think black hole.
Yes, yes, yes. So if we would like to observe the high redshift sources, the sources are very, very far away from us, 10 billion light year away from us, we need to make sure the object is has high luminosity. So only if the source is very luminous can we see it, although it is very far away from us. So the galaxy is definitely objects we like to observe, because one galaxy has 200 billions of stars. So that like one star is just like our sun. So 200 billion of our sun, that can make the galaxy, the whole galaxy, very luminous, right? But there are another source which is rare, but also can be super bright. That's a quasi-stellar object, like the right one, like quasar. If you ever take a look at a movie called Interstellar, then you will know that the quasar has through like the quasar, basically the supermassive black hole, the supermassive black hole can convert a lot of potential energy into stars. Yeah, you say it's the black hole. How can the light escape from the black hole? Yeah, the light doesn't escape the black hole if it fall down below the horizon of the black hole. But if the black hole has the accretion disk before the material falling into the black hole, the accretion disk can convert a lot of potential energy into the light. That can make the supermassive black hole very luminous. So the quasar can be very, very bright. Although the number of the quasar may be hard to find. This quasar number is small, it's rare, but this population is also very important to probe, right? If in the early universe. So the galaxy and quasars are two populations that we observe. So high is the redshift of the galaxy. Currently, state of art, we already detect the galaxy at the redshift of 10. That's when the universe is 5.5 billion years after the Big Bang. So the universe is still a kid at that time. So the most distant quasar have been observed at the redshift of 8, when the universe is about 1 billion years. Still, right, the universe at that time is very young. So that tells us, like, when the universe is still very, very young, like 0.5 billion years to 1 billion years, it already has formed very massive galaxy and supermassive black hole that's be able to emit significantly amount of photons that can travel the whole universe and allow us to observe them. So that probably means the first generation of all object, the first stellar, the first dwarf galaxies, or the first primordial black holes. We haven't detected deep enough to find them. So they probably hide in a earlier stage, basically when the universe is even younger. So how can we detect them? So we use a technique called the Lyman break selection. So what is the Lyman break? Lyman break is when the electron is orbiting around a proton, like the atom of hydrogen. When the light has a wavelength of 1,216 angstrom, then the electron will be excited from n equals 1 to n of 2. So the electron will be excited and the photon at the exact wavelength will be absorbed. And then when the wavelength of the photon has 1026 angstrom, then the electron will be excited from n equals to 1 to n equals to 3. And then the light with exactly this wavelength get absorbed. So with the wavelength shorter and shorter, if the wavelength is lower, if it's about 912 angstrom, or even or lower wavelength, then the photon will anyway absorbed by high hydrogen, and then the electron will be ionized. Basically, the photon will hit the electron, and the electron will have enough energy to escape from the proton. So that in turn, the wavelength for smaller at 912 angstrom or smaller will be absorbed. So basically, the light will change to convert the energy of a full photon will convert to the energy of the kinematics energy of the electron, basically. And so if you take the spectrum of the galaxy, you will immediately see the Lyman break, the Lyman break. Like the galaxy spectra, here is the UV, the ultraviolet continuum of a galaxy spectra. And then you see from the right frame, if you see from the galaxy, if the wavelength is smaller than 912, you can see a sudden break, because the light at the wavelength of lower than 912 and angstrom will be completely absorbed, and the light with the wavelength higher than 912 angstrom will most of the light is not observed. So and then if you see the U band, basically if you have many few filters. If U band you didn't detect the galaxy, but B band you detect galaxy, V band you see the galaxy, I band you see the galaxy, then you immediately get a sense that the Lyman break is redshifted between the U band and B band. So in the U band, you see the rest frame wavelength smaller than 912 angstrom. So, but in the B band, you already see the spectrum, so that you can immediately get the redshift of the galaxy, right? It's a 4,000 divided by 912 minus 1. That's about 3. So basically, you can use the simple feature, the break feature, the Lyman break feature in the spectrum of the galaxy to determine the redshift. So right here is a video. If the redshift is higher, then that means if you have many few filters, you will basically see the galaxy just disappear in more and more bands with higher and higher redshift, basically. And from the like from the drop-off selection, like then you know where is the Lyman break located, and then you can calculate the redshift. So people exactly use this simple technique to select the high redshift galaxies. So these galaxies are shown in the Hubble deep field. What is a Hubble deep field? The Hubble deep field is basically a very tiny fraction of the sky. Here is our eyes field of view, and we zoom in. We zoom in a completely dark sky. But if we observe it long enough, if we take very deep observations, we will still see a lot of stellar light. That's basically light from the deep universe. So every of these very tiny light is coming from the galaxies from very early universe. So the Hubble ultra deep field, we detect one galaxy that shown up in the 1.6 micron, but didn't show up in all the bluer filters, like 1.4 micron non-detection, 1.2 micron non-detection. So we know immediately the Lyman break redshifted between the 1.4 micron and 1.6 micron. So then we immediately know the redshift of the source is about 10. And we also take the spectra of the galaxies, and indeed through some modeling, basically this signal to noise is really low. But through some modeling, we confirm that the galaxy's redshift is about 10. And through the James Webb Space Telescope, we newly launched to the space. And the capability of the James Webb Space Telescope is 2 orders of magnitude higher than the Hubble Space Telescope, and we can have very high resolution spectroscopy of that source. It seems that this source has a copious the emission line of hydrogen and oxygen, something like that. So that's basically confirmed that this galaxy has a redshift of 10. And the light of this galaxy is coming from very early universe. That's basically the highest redshift galaxy we identified from the Hubble Deep Field. And these galaxies are not detected in bluer filters. If the wavelength is smaller than 1.2 micron, we didn't detect the galaxy. So that means the Lyman break has already redshifted beyond 1.2 micron. That translates to a galaxy redshift of 10. So, and then we do use the James Webb Space Telescope to confirm the redshift of the galaxy. So then that's the state of art of our understanding of early galaxy. Let's take a look of the quasar. So quasar is basically the same technique. Only the difference between galaxy and quasar is that quasar is quasi-stellar object, so it's a point source. Galaxy is resolved. It's the diffuse source. You can see the spiral arm, something like that. But the quasar is just a very perfect point source because the size of the black hole is very, very small. But still, you can use the Lyman break technique to infer the redshift of the quasar still the same if the quasar like contain a lot of neutron hydrogen, then the spectra will have a so-called Lyman break. The Lyman break allow you to evaluate the redshift of the source. So, and the first quasar has been discovered half the century ago. Right, it looks like just like a star in our Milky Way, but the redshift is very high, and the distance is large. So, and then you calculate the luminosity, it's extremely high. It's a tenth of a millionth times our sun, the luminosity. So then the guy who discovered the first black hole, Martin Schmidt, a Caltech professor, right, has shown his face in the cover of Time magazine. So basically, it's a brand new object at that time, and people have no idea the mechanism of such a luminous source. Like just like our star in our Milky Way, but the luminosity of tens of millionth times a star. So the highest redshift of the quasar we currently detected is about the redshift of 7 to 8. So you can see the Lyman break is very clear in the spectrum, in the sense that if the wavelength is lower than one micron, then you basically there's no signal. This is dark, And if the wavelengths are higher than 1 micron, then it is starting to detect something. So you immediately know the Lyman break of the source is redshifted to one micron, and then you take the spectra, you can confirm that. So that's also, and the source is a point source, and the luminosity is very high. So then you confirm that is a quasar. So the two guys who discovered these highest redshift quasars are also Chinese. They are graduate from Chinese universities, but Xiaohui Fan is a professor at University of Arizona in US, and Fei Wang is his student. It's a PhD student at Peking University across the street. So it's a very important work. Okay, so so then that's basically my summary of the maybe the first part of the talk. Like, we already identify a population of high redshift source that when the universe is still extremely young. So the redshift of these sources is about 10, and the source has two populations. One is a galaxy, one is a quasar. So the highest redshift galaxies we have identified as a redshift of 10. And the quasar is a redshift from 7 to 8. That indicates that basically at around 1 billion years after the Big Bang, there's already very massive luminous galaxy or supermassive black hole formed. So in order to get the first object, the first stellar object, you need to go much deeper in the universe. Yeah. So then the Hubble Space Telescope probably no longer can satisfy our needs. So we need larger telescope. So JWST comes. So JWST will be sensitive. It is sensitive to more infrared, basically more infrared than the Hubble Space Telescope, because if you would like to go further in the universe, if you want to see deeper space, then the red sensitivity is very important, because this source has even higher redshift. So the energy will move further toward the red. So that's beyond what we can see in our eye. It's so-called infrared. So JWST is sensitive to the infrared. It's aim to discover in very, very far away, in the youngest, in the first generation stellar object. So if the Hubble Space Telescope is, we have calculated that the capability of Hubble is about 1 billion times our eye, and JWST is about 100 billion times the capability of our eye, so that can go into very deep into the space. So the JWST can identify probably the first stellar light in the universe, as well as detect the signature of life in the basically in the exoplanet. Because the spatial resolution of JWST is high enough to be able to resolve the stellar hemisphere, the hemisphere of exoplanet and doing spectroscopy. So if the planet has life or has a human being, and the atmosphere, the movement of the atmosphere will be able to distinguished from the planet with no life. So basically, you can tell if there is a life or even intelligent life from the atmosphere of the planet. So the JWST has the spatial capability to do this for the first time. So it's an amazing telescope. So here is how big JWST is. So and here is the JWST size compared with the Hubble Space Telescope. And you can see that they fold the JWST to be able to put the JWST in a raw rocket and send it to the space. And here is the sun shield. Right, and they put the JWST telescope to the tower to do the shaking test, right? And in the end of December last year, they put this telescope into the space. And then here is a short introduction of JWST.
JWST is named after James E. Webb, NASA's second administrator who oversaw the agency's decade-long effort to reach the moon. He believed NASA had to put as much emphasis on pushing space science as human space flight. This next-generation telescope is not only 100 times more powerful than Hubble, but its ability to see infrared opens up a world of opportunities. It means that scientists are now able to detect frequencies of light that are invisible to Hubble.
The Hubble Space Telescope operates primarily in the optical, so the wavelengths that you and I can see. But as we look at the most distant galaxies in the universe, because the universe is expanding, those galaxies are, in essence, receding from us at faster and faster speeds. And that means that their light is shifted from the visible into the near infrared. So in fact, when we want to see the very most distant galaxies, the first ones which ever formed in the universe, Hubble can't see them. It's unable to see at the right wavelengths, and also it's not really big enough to see those extremely faint objects.
This shift in wavelengths is known as redshift, and the result is that the most distant objects emitting visible light are invisible to telescopes tuned to optical wavelengths.
So you need a big telescope operating in the infrared like JWST in order to see those very first galaxies, the ones which are moving so fast away from us that all of their light is redshifted into the infrared.
Now, JWST's largest program during its first cycle is going to put those capabilities to the test.
The Cosmos Web survey is going to be looking 13.5 billion years into the past, about 200 to 300 million years after the Big Bang. And what it's going to be able to do is observe galaxies that are much further away from us than we've been able to do before. So we're going to be able to find some of the earliest galaxies that have formed in the universe. The Hubble Deep Field looked at one part of the sky and stared there for a long time. And that was really our first look into the distant universe. With Cosmos Web, we are going to go a big step beyond that. So not only will we be able to look at objects that are much farther away from us and much deeper into the universe's history, we're going to cover a much larger area of the sky. So we're going to be able to observe many, many thousands more galaxies than were able to be seen in the small area of the Hubble Deep Field.
right? JWST will basically conduct a deep imaging and spectroscopy in the area of the sky about I think 2 moon, about the area of 2 moon. Why not the whole sky? Because JWST's field of view is very small. So because it's a big telescope, so the field of view of the telescope cannot be large.
Right.
So here is JWST, and here is when the first light image coming out, right? It's a big celebration in White House. So it's just demonstrate how deep you can reach for mankind currently. Here is the first image, and the arc, the light arc, is basically the gravitational lensing effect that is also proposed by Einstein, right? That the mass, the potential can bend the light, that can make the light like the long arc. And here is a JWST take a deep observation in the Jupiter extremely high spatial resolution, very pretty picture. And here is JWST imaging the death of the star and the birth of the star and the merging of galaxies, right? And the JWST zooming into a spiral galaxy. So JWST discovered a lot of very faint, very far away galaxies, very high redshift. Basically, the redshift around 10. So JWST is only observed for 2 months, and then confirmed a large population of redshift 10 galaxies. It's already the limit of the Hubble Space Telescope, and JWST will still stay there for another 10 years. So we will expect with the deep stacking of all the images JWST will provide us the deepest image we ever seen, and identify the first generation object in the universe. Here is the most farther away multi-arm galaxy that JWST have confirmed. It's actually discovered by our group, right? In Tsinghua, right? So, right here is the JWST. It's amazing. It's a space telescope. It's a huge telescope, and the NASA basically put that into the space. So, and it's infrared, sensitive to the infrared. But the only drawback of JWST, as I mentioned, it's a small field of view. So to complementary of that, we are constructing basically a large ground-based telescope. And the aperture is as big as JWST, and the advantage of this telescope is the field of view is 1,000 times JWST. So it is it's complementary to JWST. It's very fast in survey. So right now this telescope is planning in Tsinghua. So I will just briefly talk about this telescope for now. So this telescope, basically, we would like to finish it by 2029. It's actually a 6.5 meter wide field that's JWST. You can regard JWST as the narrow field, right? This telescope, because it's ground-based and it has a lot of length to correct the field of view, so it can go very large field of view. So, so this telescope will be basically complementary of all the near future telescope, like the James Webb Space Telescope and the Euclid telescope that the European agency gonna send in 2023, and the ILSST and the US community gonna build in Chile. Basically wide field imaging telescope, and our telescope will be the purely taking spectroscopy, basically complementary to the telescope who only takes the imaging survey. And also our telescope will be wide field, that making our telescope actually in a unique parameter space in the speed of spectroscopic survey. Right, it is right. It is capable of conducting the next generation spectroscopy survey in the cosmology, and help people to depict a more dynamic universe using time domain spectroscopy survey. And also it is a flexible scientific platform. So it will located in Qinghai province. It is actually in the northwest part of the China, and there's a famous city called Dunhuang. Dunhuang is a city that you can see the basically some beautiful pictures in the wall that people carved several hundreds of years ago. That Dunhuang basically is a very famous sightseeing place, and from Dunhuang it's about 200 kilometers. You get our site, and the elevation is more than 4,000 meter, and basically the condition of the observation are good. So, and also it is complementary. It's also the longitude of this telescope is complementary of all the other telescope in the world. So making this telescope a unique position in continuous survey of when the other telescope are during the day, our telescope is during the night, so still can doing complementary stuff, and also long-term monitoring of source. Right, and our president of the university have visited the site for a few times, and here, and the construction of the site is also fast. Here is a road condition in July last year. Here is the summer in 2022. Yeah, so you can see, so the road construction is very rapid. Very rapid, and local government very supportive. And we also have secured some donation, but we need more in the near future. Right, we secure about 70% of the total funding. Right, and if you have any interest in helping us, please let us know. Right, and the telescope has already made significantly progress. We have casted the primary mirror. The primary mirror casting has been done. And here is a 6.5 meter size primary mirror. And here is a small prototype wide field. Basically, all the parameters similar with the master telescope in the end, but it is a prototype, so the size of the telescope is 10% of the master, but the field of view are the same. It's allow our engineers to get more familiar with installation and the software, the control of the telescope. And so here is what we gonna achieve in the next 7 years. So we hope that through the James Webb Space Telescope and through our telescope 10 years from now, and we can basically join the force with the international community and conduct the best science result. So the last slide I would like to tour you. Basically, here is the summit of the Hawaii island, the Mauna Kea. And here is the two telescope of the Caltech and the University of California and the telescope of Tokyo University. So they are on the summit of Mauna Kea, and they are complementary to the space telescope, joining the force with the space telescope in discovering the mysterious object in deep space. So, and we hope that with the development of the master telescope, we can also join the international effort as soon as again to discover, to identify the unknown in deep space. Right, with joining with a collaborative effort with the international community. Okay, thanks. That's basically the end of my talk. Thanks.